I've been thinking a lot about Lagrange multipliers recently and sort of what value they bring to some of these Lagrangian problems. And my friend Rhett posted this really great video yesterday about what happens when an ice block falls off of a parabola. So you've got this, it's sliding down here, and the question is, would it ever lose contact? So would there ever be a point when it comes and it just kind of flies off because, the ground here can only provide a force, let us call it sort of pseudo up, right? That it can never pull it back down. And so we could absolutely do an analysis that says, show us the dynamics of something that absolutely stays in contact. But you can then look to see, well, but wait a minute, did that restoring force, not restoring force, did that force of constraint ever go in a direction that we don't actually think physically the ground could do? And so people always talk about using Lagrange multipliers to really aid in calculating that. So what I wanted to show was kind of two different ways of doing this problem. So I'm just going to cut the page in half. And so over here I'm going to do the Lagrange way. And over here I'll do, I don't know, I'll call it the normal way or something. And I want to really think about the value that the Lagrange multipliers are bringing to this, because I'm not 100% sure that they bring as much value as I had originally thought. Certainly when you talk about, oh, well, if you want to investigate the constraint force, Lagrange multipliers are awesome because they're this really, really cool way to learn about it. And, the typical examples that you do would be like a pendulum. And so if you've got a pendulum bob, right, like this, and you actually want to investigate the tension here, then Lagrange multipliers is this really, really slick way to do it where it sort of just falls right out. And I've always, sort of taught that when I get to Lagrange multipliers in classes, but it has occurred to me, especially when I do numeric solutions, that I'm not 100% sure they're the most straightforward way of doing it. So let me show you what I mean. So I'm going to say that this hill here is just some function. Y is some function of x. Okay, just some function of x. I don't care if it's a parabola or whatever it is. I'm just going to say it's a function of x. I guess that precludes it from being like a circle, which can't be defined as a function because it would be multi-valued. But, just some curve that, whatever. And then we're going to ask the question, what is the constraint force, so that we can interrogate whether it would ever fly off or not. So if y is some function of x, the Lagrange multiplier encourages you to have some g function, g equals y minus f of x, and we're going to use that g function, in the analysis here. And so what we do is we say, okay, well, the kinetic energy is just 1/2 m x dot squared plus y dot squared, super easy, and the potential energy is mgy. But we don't put in this f of x here. We just say it's mgy. We treat y as one of the variables. And then we say, the Lagrangian is the kinetic energy minus the potential energy. And then our differential equation is going to be, we're going to get two of them. We're going to be dl dx. I'm trying to think. I guess I'll do it the way Rhett does it, plus lambda. Let's see, dl dx equals ddt dl dx dot, sorry, one mistake here. So this L should be F, or G actually, the constraint function, right? And so that we get that one, and we get dl dy plus lambda dg dy equals ddt dl dy dot. And so there's a couple of equations, and then we tend to use the fact that we have this equation. So we've got that equation, this one, and this one. Those are our three equations, and we sort of monkey around with them. And eventually we're able to figure out expressions for lambda, typically in terms of, you sort of walk it all the way down to being in terms of x. And then you say, well, okay, well, these terms here are the force terms, and maybe what we'll just do is we'll look to see, we'll say, hey, look, the ground can only ever push up, right? Like, all of these arrows that I'm drawing here, they all have a positive direction of the y component. And so really we just need to look at this one here and look to see, hey, are you ever negative? Like, are you ever pulling down? And so we do a lot of analysis to figure that out. And we, do some plots and stuff to look to see if things are going to fall down. So typically what you need to do numerically, especially if this f of x is complicated, is you need to solve these two differential equations, and instead of telling the computer this, what almost is always needed, and certainly as I've done the work in Mathematica, you need two time derivatives of this. And so basically you have to sort of quickly take a couple of time derivatives of that, and be careful because this is a function of x, but x is a function of time, so it can get a little bit ugly. But then once you have two time derivatives of this box, and then you put in these two, and you're off and running. Give it some initial conditions, and away you go. And then when you're all done, you tend to have lambda as a function of time, and you know that dg dy is just 1 in this case, right? So you really just need to investigate whether lambda ever goes negative. Okay, so straightforward. And I think that it's a really cool way to find out if the ice block ever would leave the surface. So let's compare that to what I would do normally. Well, normally what I would do is I would say, okay, the kinetic energy is definitely so the same. Kinetic energy is 1/2 m x dot squared plus y dot squared, but I would immediately figure out what y dot is using this. So what I would say is that y is f of x, and so y dot is f prime of x times x dot, and then y double dot is two things. It's f prime of x, x double dot, plus f double prime of x, x dot squared, right? So I only need y dot for this kinetic energy. You know what? I'm not 100% sure I'm going to need y double dot. I don't know why I did that. We'll see. And then potential energy stays the same, except for you would write it with the f of x. You'd say mg f of x. So what you have now is a kinetic energy which has some x dots in it and some x's and x dots in it. And you've got the potential energy, which just has x's in it. And then your differential equation is simply dl dx minus d dt dl dx dot equals 0. You have a single differential equation. So that's cool. So it seems like it's a much easier numeric solve, right? You're not doing 3 equations, you're just doing 1. But then if you ask, well, wait a minute, is this thing ever going to leave the surface? Well, actually, we do need this y double dot. This y double dot is the vertical acceleration of the particle. And it seems to me all you have to do is you have to say, can you plot for me y double dot? But actually, what I want to know is like any additional acceleration beyond gravity, right? So we expect y double dot to be minus g, right? Not this g over here, but gravity. So downward plus some what I'll call the vertical constraint. So we can just figure out, okay, well, do a plot of that. Well, we have y double dot because once we solve this differential equation, we know what x is at all times, we know what x double dot is at all times, and we know what x dot is at all times, right? Because that's what the solve is going to do. So we're able to do an interrogation and say, hey, oh, all right, well, then we can calculate y double dot, and then we can look to see, like, when does it need to augment gravity to keep it in contact? So my point is that especially numerically, once you have x dot, you have x double dot, it's easy, right? It's super easy to make plots of this, and you don't have to do the extra Lagrange multiplier stuff. So what I have found is that if that's my question, like, I wonder if this ice block ever leaves, I'm not 100% sure that the Lagrange multiplier is the faster, more straightforward way of doing it. I think that this comment right here, this comment that, hey, the vertical acceleration is, of course, provided a little bit by gravity plus some other stuff, I think that that's just straightforward to have people think about. Whereas over here, the Lagrange multiplier just takes a long time to figure out what the impact is going to be. Now, when have I found Lagrange multipliers to be useful? I'll show you the one example. Let's see, can I scroll this up? The one example that I have used the most often is if I have a multipendulum. Okay, so when you do this, you've got an angle here, another angle here. Let me call it theta 1 and theta 2, and you end up with a ton of cosines and sines, bunch of trigonometric stuff. But if you do Lagrange multipliers, where you basically say, look, I have a constraint here that's L1, and I have a constraint here that's L2, it turns out you have no trigonometric functions whatsoever. You just have to pay the price of having some extra differential equations, just like you do in this situation. So, but they're relatively straightforward differential equations. There's no trigonometric functions, and I have found that something like Mathematica, it tends to run faster with more but simpler differential equations. So that's when I will reach out and grab the Lagrange multiplier approach, rather than saying, oh, hey, the Lagrange multiplier gives me this really, really unique access to the constraint force, because in fact, even in situations like this, doing this kind of trick is pretty straightforward to figure out what, for example, what the tensions are in this string, let's say. So anyways, I just wanted to post this. Rhett really got me thinking about this yesterday, and I thought, well, I would just jot it out. Hope you guys have a great day.